Assalamualaikum and hi, my name is Sintering binti Muhammad Noor from AS203. First and foremost, I'd like to thank both examiners, Dr. Nur Huda and Madam Siti Fatimah, for their time. The project title that I've been working on is effect of sintering temperature on physical structure properties of Wollastonite glass ceramics derived from clamshell and waste glass. In this video, I will go over my final year project in greater detail. This video will cover the following topics: introduction, literature review, methodology, result discussion, and conclusion of the study. Let's move on to the next slide. Wollastonite is a metamorphic mineral formed by the spontaneous interaction of calcium carbonate with silica at high temperature and pressures. Its properties include thermal stability, low thermal conductivity, corrosion resistance, chemical inertness, and a low dielectric constant, to name a few. Wollastonite is used as a filling agent in rubber, paper, and plastic, as a mating agent in paint, and as an abrasive bonding agent in ceramics. The clamshell is a part of a vast amount of litter in Malaysia, most of which is calcium carbonate. Clamshell is an excellent example of a recyclable or reusable waste product because it contains a high percentage of calcium carbonate. Clamshell is considered the greatest choice of replacing commercial calcium carbonate. Soda lime silicate glass is a popular glass composition that can be found in a variety of glass products, as LS glass is more popular than regular glass due to its optical and mechanical properties. As a result, waste materials are regarded as a method of reducing pollution while also creating a new valuable product. As LS glass is suitable for manufacturing wollastonite glass ceramics due to its high silica content. The objective of the study are to synthesize the clamshell and SLS waste glass as the base materials to form wollastonite glass ceramics via solid-state reaction method. Second, to study the effect of different sintering temperatures on the physical and structural properties of wollastonite glass ceramic. Nowadays, a large amount of solid waste accumulates in landfill sites. In general, food waste had a negative impact on the environment, resulting in solid waste pollution. In this study, formed glass ceramics are made from waste materials such as SLS glass and clamshell waste in order to solve an environmental problem. Formed glass ceramics have received a lot of attention in recent years because of their properties and wide range of applications. Formed glass ceramics have outstanding properties such as long life, reusability, and dimensional stability. The cellular structure inside softened glass particle is provided by formed glass ceramic, which is a valuable product. The porous structure contributes to the product's lightweight and is easily brittle. For that reason, the properties and effect of heat treatment on formed glass ceramics derived from SLS and CS as a forming agent is carried out to improve the physical and structural of formed glass ceramics. Researchers had stated that wollastonite has gotten a lot of press since it may be utilized in various industries, including ceramics classes, types of cement, paints, paper, and plastics. Wollastonite's distinctive properties such as its high whiteness, or low moisture absorption, low thermal expansion, low shrinkage, low dielectric constant, and loss fluxing properties and thermal stability make it useful in a variety of industries, including ceramics, chemicals, metallurgical, construction, and polymers. SLS glass waste is repurposed in this study to make formed glass ceramics. SLS glass is more popular than regular glass because of its optical and mechanical properties. Furthermore, using SLS glass waste as an alternative SiO2 supply has been linked to a glassy appearance. Furthermore, surface and subsurface damage can have an impact on the strength and durability of SLS glass. Such damage can occur when contract stresses are applied to glass surface during manufacturing, handling, and storage, though the severity of the damage can be mitigated by environmental factors. Formed glass ceramics are porous materials created by combining carbonaceous substances with glass prior to sintering. Formed glass ceramics exhibit remarkable mechanical performance and have piqued the interest of the construction industry due to the characteristics such as lightweight, rigidity, and high compressive strength, as well as being chemically inert and non-toxic. The SLS trash was recovered from the source bottles The waste glass must be washed as it is usually contaminated with dirt before crushing. After waste SLS glass is crushed into the small glass collet, the SLS will mesh with a mortar and pestle to obtain a fine powder. The glass powder will then filter through a stainless steel sieve to obtain a powder with a particle size of 45 micro. Clamshells were gathered from recycling bins. After removing any dirt from the clamshell, it must be properly cleaned, and then it will dry for a day at room temperature before being crushed and sieved into 45 micrometer size. An analytical balance was then used to weigh SLS glass and CS powder separately. According to the empirical formula in the mortar, both powders will be mixed and pounded for 10 to 15 minutes to achieve a homogeneous powder. The SLS glass powder and CS powder in 45 micro size were homogeneously combined in a ball milling jar with weight percentage of clamshell 1, 6 and 3. The mill operation required around 1 hour at 300 rpm to guarantee that both components were thoroughly combined. Then the combination will be taken out and weighed with an analytical balance of 1 gram. The 1 gram mixture will then placed in the hydraulic press to begin the pelletizing process. A total of 5 tons of weight will be pushed onto each pellet for 10 to 15 minutes, resulting in a 13 millimeter pellet diameter. After that, the sample will be sintered at 3 different range temperature, which is 800 Celsius, 900 and 1000 Celsius. The pellets will be grounded into a fine powder after the sintering process for further analysis. After finishing the basic sample preparation, I proceed to examine their physical and structural properties, which is the density, porosity, linear shrinkage, SEM, EDS, and FTIR. This is the machine provided by the university laboratory that students can be used after getting the permission from the laboratory assistants. This figure depicts the effect of different treatment temperatures on the part density of formed glass ceramic samples. When sintered at 800 and 900, the part density of formed glass ceramics increased by 1% from 1.102 to 1.227. However, the trend has reversed when the sample was sintered at 1000 Celsius, where the density of the sample decreased to 1.035. It is clear that the progression of the porosity is dependent on the trend of part density. The linear shrinkage decreased as the part density increased for the progress in sintering temperature between 800 and 900 Celsius as shown in the next figure, but it differed at 1000 Celsius where the linear shrinkage decreased as the part density increased. Most likely, the excess gases produced by the clamshell accelerated the progress of the internal pressure inside the part sample, resulting in the overload pressure. This phenomenon resulted in the rupture and a release of the pore walls. This figure depicts the total porosity of 136 weight percentage samples sintered at various temperatures for 60 minutes. The trend of the part density result and the SEM micrograph have a linear relationship. This is due to the fact that the density of formed glass ceramics is linked to pore formation within the glass matrix. According to the result, the highest amount of porosity can be found in the pellet at 800 Celsius heat temperature due to the high percentage of CO2 from the clamshell being released during the forming process, which produce the glass matrix within the formed glass ceramic. However, at 1000 Celsius heat temperature, the size of the formed glass ceramics get really small. The porosity for the pellets also hard to be found, and the color of the sample becomes different, which is dark yellow color. This is because as the softening temperature becomes greater, the viscosity of the liquid glass will also become greater, which affect the pores with a small diameter to become moderately hard to grow up. Although some calcium carbonate remains accessible for forming on the surface, the interior becomes inhomogeneous due to a high amount of gas formed from carbonate disintegration, preventing porosity from being formed efficiently. The linear expansion of the formed glass ceramic sample against heat temperature was shown in the figure. For 1% clamshell composition starting from 800 Celsius, the graph show a decreasing pattern in the linear expansion of the sample. This pattern continues until 1000 Celsius where the linear expansion begins to decrease. This is due to the porosity formed during the forming process with heat treatment temperature of 800 Celsius until 1000 Celsius caused by CO2 gas released during the sintering process. Thus, the samples tend to expand according to the viscous liquid phase formation. In the range of temperature approximately between 800 and 1000 Celsius, the CO2 gas release related to the calcium carbonate decomposition is quite similar to the commercial calcium carbonate. At temperature above 900 Celsius, the viscosity of the pellet begins to decrease, resulting in the minimal porosity in the structure and the sample becoming compact. At 1000 Celsius and above, the glass viscosity is sufficiently low for expansion to occur, and as a result porosity to form. Glass experience significant shrinkage and gasification at this temperature. However, the sample's linear expansion at 800 Celsius is greater than that at 1000. This pattern is identical for sample containing 3% and 6%. The chemical composition of SLS and CS raw materials were analyzed by using energy dispersion spectroscopy, which is EDS. The elemental analysis was shown in the two figures below. As can be seen in the table inside the figure, clamshell contain a very high amount of Ca, C, and O, while in the pure SLS, it contains major component of Si, Ca, O, and natrium. Other elements such as aluminium, magnesium are minor constituents contained in SLS composition. Figure 8 shows the SEM micrograph of the formed glass ceramic samples in parallel cross-section sintered at various temperatures for 60 minutes. The results are used to visualize the microstructure details on the surface crystallization of the sample. As can be seen in Figure 8A, B, C, the pore structure are slightly different in the cross-section of the sample's microstructure at 1 and 6 weight percent samples sintered at 800 Celsius. This is because the gas generated by the forming agent at 1 weight percent give insufficient pressure to cause the expansion on the glass matrix than 3 and 6 weight percent. The pore structure begins to become larger and well formed for 6 weight percent sample as shown in Figure C. At 800 Celsius, the SEM micrograph shows that the 6 weight percent sample has the largest pore structure with the thickest pore walls. Figure 8A shows that a 1 weight percent sample sintered at 800 Celsius has smaller pores with homogeneous pore distribution than a 6 weight percent sample sintered at the same sintering temperature. As the sintering temperature rises to 900 Celsius, the number of pores decreases, indicating that the glass has densified. It agrees with the calcium carbonate decompose rate because the result shows that there is no reaction after 800 Celsius. Furthermore, low viscosity affects pore formation because pores tend to rise to the top of mold, resulting in inhomogeneous pore distribution. When low in temperature, the viscosity of matte glass is increased, making difficulty of gas expansion. Hence, there is little changing the volume of the formed glass ceramics. FTIR spectra of 1, 3, and 6 weight percent samples sintered at various temperatures for 60 minutes shown in a Figure 9, 10, and 11. The IR absorption band and formed glass ceramics band assignment for 1, 3, and 6 weight percent can be seen in the table 4. Based on the figure shown, at the wave number 400 to 600, the presence of CAO stretching vibration mode occur. The presence of CI bending and stretching mode with numbers in the range of 800 to 1000 cm in every sample sintered at different temperatures confirm the presence of the silica contained in SLS glass powder. A promising material to be used in the construction industry, formed glass ceramics have been successfully fabricated from a waste material made out of SLS glass and clamshell by solid-state process. The physical and structural appearance of the formed glass ceramic were greatly influenced by the sintering temperature and percentage of clamshell content. In terms of structural properties, increased clamshell content result in fewer pores due to high densification of the glass matrix. The density and porosity of the glass ceramic samples influenced by the SEM of the glass ceramic forms, which reveal glass structure with predominantly open porosity. Furthermore, the highest crystal phase content such as Wollastonite will obstruct form formation and have an impact on the properties of formed glass ceramics, which are influenced by the crystallization process in the glass map. To summarize, the production of formed glass ceramics with porous structures derived from waste materials will benefit both the economy and the environment. Depending on the type of porous structure, it is a useful material for a variety of applications in the industry.